Today we're going to be looking at CSD materials, but why do we want to think about crystals in solid forms and solid form stability? In a lot of chemical industries, particularly in the pharmaceutical and agrochemical industries, solid form selection is really important in product development. So, for example, the solid form can impact a range of different properties and can change how products need to be processed. It can change chemical and physical stability, crystal shape, mechanical properties, particle control, solubility, and melting point. Luckily, in the CSD, we've got a wealth of information about different forms of structures. For example, different polymorphs, different solvates, hydrates, salts, co-crystals, and we can use this information to give us insights into solid form and solid form selection. So we saw that the CSD now contains over 1.1 million structures. And if we dig a bit deeper, we can see some of the different types of solid forms available. So here you can see the growth of co-crystals in the CSD, and they're color-coded by their complexity. We can see how many different solvates, hydrates, polymorphic families, and ref code families we have, and we've also got a number of different salts. And when we think about solid form and how we want to change the solid form, all of this information is going to be valuable to us. So if we investigate just one of the molecules in the CSD, we can start to build up a solid form landscape for that molecule. So in this fluconazole molecule in the middle, we can see in the CSD we have multiple different polymorphs. So that's where the molecules arrange themselves in different ways in the solid state. We've also got different solvates, different salts, as well as co-crystals and hydrates. So the diversity of the solid state that you can get for a relatively simple molecule can actually be really quite complicated. So being able to understand what's going on in each individual structure becomes really important. And it's certainly important in terms of stability, and getting the assessment of stability wrong can have really adverse effects further down the line. So here's an example in real life where it did have adverse effects. So back in the 1990s, I think, there was a HIV drug called ritonavir, and it was already marketed and being used by patients worldwide, and that actually changed form. And the form that it changed into didn't have the same properties as the marketed drug. So it had a huge impact on the pharmaceutical company, who had to quickly withdraw the drug. But it had an even bigger impact on the patients who were relying on this drug for treatment. We can see here there are different interactions going on in the different forms. And actually, the new form was found to be more stable. So we need to think about what we can do and how we can use structural informatics to help decrease the risk of this ever happening again. So we can think about stability of crystals in the same way we would think about the stability of a brick wall. And we can use information around us to help inform us about what arrangements, in this case, bricks need to be stable. And we can use the frequency of observations to indicate the stability. So if we do that for brick walls, we can see that the Great Pyramids have got, if you can see it on my slide, this formation of stones or bricks. If we move over to Hadrian's Wall, we can see that they've got a similar arrangement of bricks. Great Wall of China, again, we're seeing this Form A arrangement of bricks. My house from 1967, we're seeing Form A of bricks. The CCDC building in Cambridge, 1992, we're seeing the same formation of bricks, although it looks a bit more like a co-crystal at CCDC. So our database of walls indicates that A is the most frequently observed arrangement, and therefore, because these walls still exist and we keep using this formation of bricks, we can predict it's the most stable form. we can use this approach and we can go back to our ritonavir example and look at things like hydrogen bonds to predict what the likely and unlikely interactions could be. And by using functionality available in CSD materials, then we could have actually predicted that perhaps the marketed form wasn't the most stable. So by applying these techniques early on in the process, we can mitigate those risks. And if we think about the different characteristics that influence the stability of a solid form, then we can see things like molecular conformation have an impact. We can see that hydrogen bond interactions, intermolecular interactions, and symmetry all have an impact on the stability of our crystal form. So our CSD portfolio helps you search, visualize, analyze, and generate new insights from the CSD. And today we're going to be focusing on CSD materials and particularly the functionality available through our Mercury software. So here you can see some of the components: crystal packing, motif search, hydrate analyzer to do detailed structural analysis, our CSD conformer generator to help with solid form design, and then a range of different software and different functionality to help solid form risk assessment.